In this screencast, we're going to learn about curve fitting and talk a bit about minimization and optimization in general, but with our focus being on curve fitting as we've discussed in class, and we'll discuss more on Wednesday. So we're going to cover a lot of stuff here. There's a lot of details, so this might be kind of long, but it will hopefully contain everything that we need to know to be able to fit anything we want. Okay, so let's start by loading up the appropriate module. So SciPy optimize. Again, give it a short name. So let's call it opt. As we've done before. So we've seen this before. We've used this. In fact, we've used this when we talked about scalar functions or root finding for scalar functions. Okay, but there's a lot of other stuff in here, most of which we're not going to talk about. Okay, so there's optimization routines, do minimization, something called least squares, which sounds interesting. Constrained minimizations, non-negative least squares. Okay, other sorts of minimization stuff, other things. And then for fitting, there's curve fit. Now there's a lot of routines here because optimization, minimization is a general problem of tremendous importance. There's a wide variety of cases where we want to do things. And to do minimization or optimization, particularly for nonlinear functions in multi-dimensions, is a hard problem. We're going to encounter an aspect of that when we do a nonlinear least squares fit example. We'll see some of the issues popping up. And so, again, there's lots of techniques for dealing with this and trying to improve how things are handled and whatnot. And that's what a lot of these routines do. So I will, encourage you to look at these on your own. For us, though, we're going to focus on curve fitting. Okay. So let's start by looking at this least squares routine. There we go. Okay. Again, lots of arguments. We've seen things like this before: a function, some x0, some optional arguments, and a whole bunch of things. This sounds like it does what we want it to do, and it does. Okay, this minimizes the sum of squares of a set of equations, okay, which kind of sounds like what we want. Here it even tells us what that means. Okay, it minimizes the sum of some function squared. Okay. Well, that's exactly what we're doing with chi-squared fitting, although we're doing a special function, okay, not just any generic function. So this is a more general routine that allows us to not just minimize something like we do in least squares, but minimize any sort of function squared, or any way that we want to define distances. Again, for our purposes, we have a special case in mind, and so although we could use this general routine, we're not going to. So that's all that I'm going to say about that one. Okay, again, if we wanted to solve more general things, it's a great thing to use. Okay, and we could use it for what we want to do. But since we're doing fitting, and that this means a specific thing, there's a specific routine for it. Okay, curve fit. So this does a nonlinear least squares fit of a function f to data. Well, that's exactly what we want to do. It even tells us that data is equal to f. F is some function that we pass in, that's our model. Okay, y data we pass in. X data is the x values at which we evaluate our function. And then parameters. Okay, uses this funny notation that we're going to see a few times, and we'll talk more about and understand in a little bit. Okay, this data is, so it's the function evaluated at this plus potentially some offset. Okay, this offset will be represented by the errors in our measurements. Okay, those errors can be passed in sigma. Okay, as it says here, sigma, if it's not none, is the relative weights in the least squares problem. In other words, it's the error bars. Okay, it's the weighting is 1 over sigma that we're using. Okay. P naught, as it says here, again is optional. It's an initial guess for the parameters. Now we saw when we talked about least squares fitting to a line, we didn't need to make an initial guess. We could directly calculate the best fit parameters. While that's true for linear least squares, that's not true for nonlinear, because then we're solving a nonlinear system of equations. And that's where difficulties come in and where this P naught is going to be important. Okay. What does this return? Well, it returns p-opt, the optimal set of parameters. It even tells us what that means. It's the sum of the squared error of this thing, the function evaluated x data, and the arguments or the parameters, okay, minus the data. In other words, it's the least squares. It's the chi-squared being minimized, giving us the least squared. Okay? So these set of parameters will be the ones that satisfy that condition. It also returns what's known as the covariance, or the covariance matrix for this. The important pieces of this are the diagonals, which provide the variance of the parameters, and we'll talk about that a bit more in a little bit. It tells us we can look at least squares, and then it gives some examples, but we're just going to do our own. So you can look at those examples on your own and play with other cases that you might be interested in. But let's do a model of this by defining our own function. So we'll just call it f to make it simple, to make its name simple, and it'll be a function of 3 parameters that we'll just call a1, a2, a3. Okay, this function will make up a function that's highly nonlinear, so it will be the square root of a sine squared, as we write here, plus a2 times the cosine of another parameter, n squared, and close off the square root. There we go. Okay, except of course I did something silly. I didn't actually return anything, so let's return something. Okay, so that's our function. Let's pick some random data points. Let's pick 20 data points between 0 and 2. Okay, so imagining that we make measurements at these data points. We'll calculate a set of true values, which is our function evaluated at these points with some set of parameters. Now I've defined a set of parameters already. I'm not going to tell you what they are yet. They're stored in the array a true. So we need to pass in the 3 parameters. So they're a true 0, a true 1, a true 2. Okay, so that gives me a set of y true. Now, I had to specify things this way because this takes 3 parameters. Okay, if I had just tried to pass in a true, okay, this doesn't work. A true gets interpreted as a1, happens to be an array of three things, but who cares? A1 is that. So this complains and says, but the function wants 4 arguments, but you only gave it 2. Okay. The problem is that a true is treated as an array, well, as it should be because I've passed it in as an array, just like x. Okay, so x correctly gets interpreted as an array, but we wanted a1 to just be a number, not an array. Well, that's where this notation is useful. Okay. The star means don't treat this as a single array, but expand it out, okay, in terms of its 3 components, or in this case 3 components. So this really is the same as what we have typed out here. Okay, it just expands it out in terms of its components, and so it does treat each one of these as individual things that are passed in, which is exactly what f wants. Okay, so we should see that the y true we get here is the same as we had gotten when we wrote it out by hand. So this is a nice, convenient thing that makes manipulating these types of things much easier. So we will use this frequently. Okay, great. Now these are the true values, but of course if we make a measurement, the measurement isn't going to give exactly these values. There's going to be errors on them. So let's invent some errors. Let's suppose that there's 10% errors. Okay, so what that means is that our error at each point is 10% of the true value. In other words, we're going to allow fluctuations to be Gaussian with a width, sigma, of 10% of the true value. We can now generate data, okay, which are the true values plus some Gaussian random fluctuation. Well, we can generate Gaussian random variables using rand n, and we want the same number as we have for for y true. This, of course, generates Gaussian variables with sigma equals 1. We want sigma to equal what we have here, so we just multiply by sigma. And this is our data. Okay, so this is the data that we're going to try to fit to our model and extract our parameters. Okay, great. Well, it'll be useful to plot this data. We know if we use plot, we can, well, plot the values, but there's also error bars associated with them. And so we would like to also plot error bars. Well, not surprisingly, there's something that does that for us. Also, not surprisingly, it's called error bar. So if we look at error bar, It behaves an awful lot like plot. We feed it x and y. We can feed it y errors and x errors. Okay, we don't have to. Defaults are not to have those errors, but we can feed those in. We can specify the format that they appear. By default, it plots things as a line, which is kind of a funny choice. Okay, and there's a whole bunch of options here for how we control the error bars, their colors, their thicknesses, whether we have upper and lower error bars on them for both x and y, whether we plot them all, their thickness. Okay, so there's all sorts of things that we can set, and there's more details about these below. Okay, so we can really control everything about the error bars. Okay. Furthermore, when we pass in these x and y errors, we can pass them in as a number, if there was the same error for all the points, as an array, one for each of the data points, and then it will plot that as an error bar. Okay. If we only pass in one number per point, it assumes we have a symmetric error bar, okay, which is true for Gaussian errors. We can also have asymmetric error bars, where the error bar above and below, for example, in the y direction, are not the same. Well, then we pass it in as a two-dimensional array, or 2 by n array. Okay. And again, it explains all of these sorts of things. Okay, we can also have upper and lower limits. We can do all kinds of well, pretty much incredible things. Okay, this can pretty much do it all. Okay. It takes other arguments besides those. All the other arguments are also listed here, and you should compare those to plot. They're basically the same thing as plot. Okay, so this really is, in some sense, just a wrapper around plot to also include error bars. Okay, so again, let's go back up. The main thing, x, y, error bars, and format are the things that we're going to play with. All the rest are other interesting things that we can also play with, but we won't do so. So let's do this. We want to plot x and y. Y error is what we had called sigma. For format, let's make it black disks. And let's give this a label. Call it the clever name data. Okay. So we plot that. Whoops. And we make an error because we don't call it the right thing. There we go. Okay. So here is the data that we have plotted. Okay. Our data with our error bars. Now we know what the true model is here because we've generated it. So let's plot the true model, and let's plot it finely gridded. So let's make a fine gridding of this. So we have x values from 0 to 2. I don't know, let's make 100 of them. Let's plot x and our model, evaluate at these points and at the true points. Okay, let's make that a black line. Give it the clever name true. Okay, and this is what the real model looks like. Okay, or what the model from which the data was drawn. Okay. Now we should be able to just look at this and see whether it makes sense or not. Okay. What that means is these error bars are supposed to, be a true reflection of the error in the data. We know that these are Gaussian errors and they're 1 sigma error bars, which means that 68% of the time our data point should fall at least this close to the line. And so if we look at the data, the line should go through the error bars, cut through them, or be at least that close to our data point about 68% of the time. Now we have 20 data points, and 1 sigma is 68%, so we expect of order 14 of the data points to go through, for the line to go through the error bars. So maybe about 6 or so to be outside that. Okay, we have a small number of points, so we're going to have large fluctuations in this. It's not going to be exact, but it gives us an idea of whether this curve makes any sense or not. And so if we look at that, this one is just outside, this one's just outside, there's a couple here that are outside, this one's very close, so there's 5 or 6-ish that are outside. So that's quite reasonable. In fact, we expect in general that 95% of the points should be within 2 sigma. So if I double these error bars, the curve should go through the doubled error bars 95% of the time. Okay, so in this case, it looks like probably all of them are within that. So we don't have any really crazy fluctuations in this random data set. It wouldn't be unreasonable to have one of these points off even more than it is. Okay, but we wouldn't want a whole bunch of them because then that wouldn't be a good indication. On the other hand, if this line went too close to the center of all the data points as compared to the error bars, that would also be disturbing. Tell us something about the data, at least the error bars, not truly reflecting our errors. Whether that's because we've overestimated the error bars or cheated would be an important question. Okay, but for us, we now have this. So we're going to want to do a fit. So let's again look at curve fit. We feed it in F, our X data, our Y data, and we have errors, so we should feed those in too. Okay, so let's go ahead and do that. So we have our function, our X, our Y, and our error bars were stored in sigma. And so we run this, and it reports some stuff. Okay, reports our best fit parameters and our covariance matrix. So let's store that in something. Let's call this A1 and C1. C1 for the covariance matrix. So A1 is our best estimate of the parameters, and C1 is our best estimate for the uncertainties in these. We can extract the uncertainties, as the documentation suggested, by looking at the diagonal of this. And in fact, we want to take the square root of the diagonal. Okay. These should be the error bars in these values listed here. Okay. They're reasonably good. I mean, these values are big. Error bars are tiny. Okay. The error bar is bigger, but I mean, we don't really know what to expect right now, so that doesn't look terribly crazy. So let's go ahead and plot this. Okay. So let's plot the same thing, but now for using our new set of parameters A1. Let's make that a red dashed line, and let's give it the clever name try1. Okay. Now if we look at this, again, the same arguments we made before should apply. Okay, we should expect that if this is a good fit in a true model, that roughly 68% of the time, this should go through the error bars of our data points. Okay, so there should be, a handful of them, 5, 6, 7 or so of them, that's not true. Well, I don't know. This one doesn't. These 3 don't. These 2 don't. There's at least 3 here that don't. There's at least 3 here that don't. That's a lot of points that this doesn't go through. Okay, this does not look like a very good fit. Okay, now we've kind of cheated because I've drawn the true one in here, which the dashed line doesn't look like the solid line, so that is somewhat misleading because in principle we don't know what the solid line is. Even if that weren't there, though, we would worry that this doesn't look like a very good fit. Okay, so let's stick the legend in there to remind us of what we have. Okay. Now, doing this by eye is not the best way. Okay, we can actually calculate what the chi-squared is. Okay, well, the chi-squared is the sum of our data minus our model. Okay, evaluated with these sets of parameters squared divided by the uncertainty squared. Okay. So we can calculate this thing, and we get a value of 163. Well, is that good or bad? Well, to know whether this is good or bad, we have to compare this to something. Compare this to what we expect. What we expect is that the chi-squared should be approximately the number of degrees of freedom. What's the number of degrees of freedom? Well, it's the number of data points. That's the length of y, minus the number of parameters. That's the length of A1. In other words, we know there's 20 data points, we know there's 3 parameters, so this should be 17. And lo and behold, it is. Okay. 163 is not very close to 17. This is a bad fit. Okay, this is a bad chi-squared. Okay. We can quantify that even further by checking the goodness of fit. The goodness of fit is given by the complement of the incomplete gamma function, as discussed in class, at least on Wednesday. That's contained in SciPy special. It's a special function, so let's import that as SF. So there's the gamma inc c is the incomplete complement of the incomplete gamma function. And again, as discussed in class, this is degrees of freedom divided by 2, being careful to get a floating point answer, and the chi-squared divided by 2. So what this tells us is the probability that our data was drawn from this model. That is the model with this set of parameters. So let's calculate this. Yeah, so this is 10 to the minus 26, 10 to the minus 25. This is telling us that the probability of this being a good model is 10 to the minus 25, or one time out of drawing the data or doing this observation 10 to the 25 times, we might expect to get data that looks like this from this model. That's not very likely. Okay, this is not a good fit. These parameters do not accurately reflect the data. But it minimized the chi-squared. So how did this happen? How could this, possibly give us the wrong answer? Well, it's giving us the wrong answer because of what I said at the beginning. Minimizing a nonlinear function in multi-dimensions is hard. Okay? What's happened here is it has found a minimum in the chi-squared. Okay? Notice I said a minimum. It's not found the global minimum. So the algorithm did the best that it could. Okay? It wandered around in parameter space, got close to this point, and then found that, aha, there is a minimum around there, and here it is. It's not a very good minimum. Okay? It's very far from the real minimum, okay, because this curve is not really at all that close to the data, but it is still a minimum. And this is the problem. Finding local minima in this complicated space, okay, is easy. This is like saying you're in very hilly terrain. Find the lowest point. Well, where you're standing, you can walk to the lowest point that's near you, but how do you know that that is the absolute lowest point amongst all the hills? You don't. Okay, you started at a particular point and walked to the closest point, or the point nearby that you could see that was the minimum. That's what the algorithm has done. Okay? And that's the difficulty of doing these nonlinear minimizations, okay, in multi-dimensions. That's why there's a P0 in here, okay, to allow us to start closer to the true value. Okay? If we don't specify that, then it assumes they're all ones. Okay? And so, I mean, this is just a fundamental problem and limitation with doing this sort of problem. We need to know something. We need to know how, when, where, whatever, what a good starting point is. Or we need to try lots of starting points to try to hone in on the global minimum. Okay? Again, this is a minimum. Okay? In the neighborhood of these points, it just happens not to be a very good minimum. Okay? So we need to somehow know what the true value is. Okay? If we're doing a real observation or a real thing, we hopefully have some idea of what the real values are, so we can start somewhere close to those values. Now, in this case, we do know what the answer is. Okay? Here's the true answer. In fact, this fit did a pretty poor job of getting anywhere near this. Okay, A2, the second parameter, not so far off. But these other two are horrible. To do a better job, then we need to specify some initial starting point. So let's pick some initial starting point. Okay? So, the one that it started with was 1, 1, 1, okay, which really doesn't seem that far away. And so this again is a dangerous thing with these nonlinear minimization problems. Is even if we start not so far away, we can wander a far distance. Okay, we wandered from 1, 1, 1 to this point to find a local minimum. So we're going to have to start with an even better guess. So I don't know. Let's try 0.4, 0.3. Okay, now let's see what we get for A2. Okay, better. Okay, these are more reasonable in some sense. Certainly they're not these huge numbers, but this still really isn't that good of an estimate. Okay, I'm not going to plot it, but we now know how to calculate that. We can calculate the chi-squared for this set of parameters, and we can look at it, and we see that it's 56 or 57. Okay, that's not that close to 17, the number of degrees of freedom. We can again quantify that by calculating the probability, and it's 10 to the minus 6. So that's still not very good. Okay? So we started significantly closer to the true value, but still wandered away. Okay? Let's start even closer. Okay? Okay, that's starting to look more reasonable. Okay? Let's again calculate the chi-squared and look at it. 9. That's actually pretty good. Okay? We can calculate the probability for that. 90%. Okay? So that's a really good fit. Okay? Or at least it appears to be a really good fit. Let's plot it. Okay, so let's plot A2. Let's make it, I don't know, green dash dot. Call it try 2. Update the legend. And now we see that this dash dotted line goes through the data extremely well. Okay, in fact, it fits extremely well, almost too well. Okay, this chi-squared is actually kind of small, maybe even smaller than we might have expected. Okay, which is actually telling us something about the data. Didn't fluctuate very far away from the true line. In fact, it was kind of surprisingly close. Now you'll notice that this A2 that we got is not exactly A true. Okay, so it doesn't return exactly the true values. Okay. It returns an estimate of them with some error. We can calculate what those errors are. Okay, and they're given by this. Okay. This is a somewhat interesting case. These are the 1 sigma error bars. So what that means is that, we expect that the true value is this plus or minus this at 1 sigma, so at 68%. Okay. These values that we calculated actually deviate surprisingly, well, more than I would have expected from the parameters. Okay. But, it happens. This is the nature of doing fitting. Okay. So these are our best fit parameters to this data set given our model. Okay. Again, they're not exactly the same as A true. Even so, this is a good fit. Okay. Again, as I said, perhaps too good. Okay. The chi-squared is surprisingly small. What is useful to do, or useful to compare this to, is the chi-squared for the true model. Okay. So if I calculate the chi-squared for the true model, let's just call that the chi-squared, put in A true here, you might ask yourself the question, what do you expect the answer to be? Okay, so let's go ahead and calculate it, and let's look at it. Okay. Notice that it's larger than the chi-squared that we calculated for the best fit model. Well, that better be true, otherwise our best fit should have been the true parameters. Okay. We don't expect to get exactly the true parameters back because there's errors. Okay, there's fluctuations. The data does not exactly follow the curve. It's fluctuated around the curve. And how it's fluctuated around the curve is going to drive these parameters to be slightly different values. Okay. And so, in fact, we found that the true model is not the best fit. In fact, it rarely is. And in this case, the data has fluctuated in such a way that it's actually moved, the curve more than I would have generally expected. And in fact, if we run this again, in fact, you should run your own case, and you should find, somewhat different results. And in general, these parameters are typically closer to the true parameters, certainly within 1 or maybe 2 sigma. Here we, for whatever reason, have much larger deviations. But anyway, this is the nature of doing fits, and the things that we have to run in, that we do run into and have to deal with when we're calculating fits of data. In this case, I've chosen a particularly bad nonlinear function. Okay. In practice, we probably wouldn't fit this function to the data. The square root, why are we taking the square root here? Okay, we might as well square this and square the data, and then this function won't be quite so hideous and not so nonlinear. Maybe that would lead to a better fit. Okay. Of course, if we do that, we have to be careful to make sure that we change the error bars appropriately, because These are the error bars for y, not y squared. But again, we know how to do that. Okay, so again, there's lots and lots of things that can and should be done when we're fitting data. This gives us an example and at least an introduction to how we go about doing such things. And now we can play with lots of examples of this, such as we'll do in the homework and in the lab.